right, so here we are. We're doing some extra practice on substitution. So here's my first problem. I'm going to do some substitution on this one. This is a classic example of a structure of the problem that we should recognize. I have a fraction where the denominator is a quantity raised to a power. So I'm going to rewrite it so it's a little more clear. I have 7x squared plus 3 to the negative fifth being multiplied by an x and a dx. That x right there is from the numerator if you're wondering. So it looks like I have two things multiplied together where one of them is a quantity raised to a power or a composite function, so I'll let that be u. So u is 7x squared plus 3. If u is 7x squared plus 3, then the differential du is going to be the derivative of that, or 14x times dx. Now clearly the 7x plus 3 matches, but this does not match that. I've got an extra 14 there, so I'm going to divide through by 14. I'm going to clean that up a little bit, massage it algebraically to make it work, and that's going to become 1/14 du is the x dx. I can always fix a missing coefficient. I can't add or subtract something. I can't fix a missing variable, but I can fix a missing or a wrong coefficient by just multiplying by the appropriate value. Now I'm going to do my substitutions because this now matches. Right? And that's going to give me then the integral of u to the negative 5 times 1/14 du. Right? The 1/14 will get pulled out in front, so I'm going to have 1/14 times the integral of u to the negative fifth du. Both things that are supposed to happen with substitution happen. That is, the x is all turned into u's, and something the argument or the integrand that is left is something I can easily integrate. So let me go ahead and integrate that. 1/14 times add 1 to the exponent is a negative 4, so u to the negative 4, and 1 over negative 4 goes out in front, and of course plus c. I might be tempted to leave it like this, but it's not correct. The problem started as an indefinite with x's. It needs to end with x's, so I'm going to do a back substitution. I'm also going to clean this up. 4 times 14 is 56, so negative 1 over 56 times the quantity 7x squared plus 3 to the negative fourth plus c. And there's my problem solved using substitution. Okay? All right. Another problem. Let's see if we can make sense of this one. Again, another classic setup. I have an exponential term, and the exponent is a function itself. Let me rewrite this so it's a little more clear. I have e raised to the 3x minus 9x squared, and this is being multiplied by 1 minus 6x dx. Right? Here's my composition. There's the inside of the composition, so that's what I'll call u. I'm going to check and see if this works. So u is 3x minus 9x squared. If that's my u, then my differential d will be the derivative of that, which will be 3 minus 18x times dx. Now clearly this does not match this, but do you see how if we factor the 3 out of the orange, we could make the two match? And so that's going to give me 1/3 du is 1 minus 6x dx, and now I have it matching so that I can perform my substitution. So the original integral is going to become the integral of e to the u times 1/3 du. Okay? Pull that 1/3 out in front. I have 1/3 times the integral of e to the u du. That's the integral I can do. The integral of 1/3 e to the u du is going to be 1/3 e to the u plus c. I can't leave it like that though because I'm not allowed to have u's. My problem has to have x's, so I need to do a back substitution. So then my final answer is going to be 1/3 e to the, what was u again? Oh, that's right, 3x minus 9x squared, and of course plus c. So I'm just doing substitution problems, one after another after another. But I'm looking not for the individual problem, I'm looking for the structure. Quantity in the denominator raised to a power. Exponential term with a messy exponent. Right? What do you see here? Oh, hey, what do you know? It's another exponential term with a messy exponent. So what worked last time will be what I'll try this time. If you're having a hard time seeing it, let me rewrite it for you. It's e to the negative 4x cubed multiplied by 11x squared dx. There's the messy, I don't want to do that. There's the messy exponent, so that'll be our u substitution. So we will say that u is equal to negative 4x cubed. Then the differential d would be the derivative of that, so that'd be negative 12x squared dx. Now this one is a little trickier than most, because while this doesn't match, I can still make it happen. Okay? But it's not going to be as simple as just dividing by negative 12. I have to divide by negative 12 and then multiply by 11. And so that's going to give me negative 11 twelfths du is equal to 11 x squared dx. Okay? So I'm going to divide through by negative 12 and multiply by 11. Okay? And now this matches, so I can do my substitution. My integral is going to turn into the integral of e to the u times negative 11 twelfths du. Pull the negative 11 twelfths out, but do everything in one step, and I get negative 11 twelfths e to the u plus c. Again, this is almost done, but I need to deal with that u. I need to do a back substitution, so then my final answer is going to be negative 11 twelfths e to the negative 4x cubed plus c. All right, next problem. Okay, so, what a mess. I'm going to rewrite it because I think it's ugly how it's typeset. So I'm going to say that this is the integral of 5 e to the 1 over y divided by 3y squared dy. Now, I'm not sure what's going on here, but I'm seeing something I've seen before. I'm seeing an exponential term with an ugly exponent, so maybe that's the key. So I'm going to snatch some things and move some things around here and see if I can make this make sense. Could I do this? Could I call this 5/3 just to get those numbers out of there? E to the 1 over y times 1 over y squared dy. Now, and if you're wondering why I did this, it's because those things are just annoying me, and since they are a coefficient, I can always pull that coefficient out in front of my entire expression. Right? And so now I'm going to try substitution. I'm going to try substitution with that being my u. So if u is equal to 1 divided by y, then the differential du is going to be the derivative of that. So that would be negative 1 over y squared dy. And I've almost got that right here. I've got positive that, and I need negative that. So could I just, make this side positive and make that side negative and call it good? And then do my substitution. So the 5/3 didn't get substituted, so it's still there. The integral of e to the u times negative du, but I can just move that negative out in front, and then that's negative 5/3 integral of e to the u du. Integral of e to the u du is just e to the u. So that's going to give me negative 5/3 e to the u plus c. And then back substitute because u was 1 over y. So I've got negative 5/3 times e to the 1 over y plus c. So what looked hard ended up being not so bad because I'm following a pattern. I saw an exponential term with an ugly exponent, use the ugly exponent as u and see what happens. Wait, you want to do more? Okay, here's another classic pattern to see. Do you see two things multiplied together? Do you see one of them as some junk raised to a power? As a term raised to a function raised to a power? Function raised to a power? The function is almost always u. Let's see if it works. U is equal to 2 plus t to the 4th, and the differential du is going to be the derivative of that, or 4t cubed dt. Well, this almost matches. I just got to get rid of that 4, so I'll divide through by 4. So 1/4 du is equal to t cubed dt, and now this matches perfectly, and I can do my substitution. When I do the substitution, I get the integral of u to the negative 1/5 times 1/4 du, move the 1/4 out in front to make things look nicer. 1/4 u to the negative 1/5 integral of u to the negative 1/5 du. Both things that are supposed to happen happen. That is, all the x's went away, and I've got something simple to integrate. Okay? When I say simple, I don't mean easy. I mean uncomplicated. Add 1 to the exponent will give me 4/5, so multiply by 5/4 out in front, and of course plus c. Oh my God, I love this stuff. That's going to give me what? 5/16 times the quantity 2 plus t to the 4th. I'm doing my back substitution, raised to the 4/5 power, and of course plus c. My God, these are fun. Last one. Oh, wait, last one on this page? No, wait, are there more? Oh my gosh, there are so many more. There are, how many more? Oh my gosh, many. 1, 2, 3, 4, 5, 6, 7. 7 more problems to do. This is great. I love this stuff. Okay, that make you dizzy enough by doing that? This one's tricky. I'm not even going to lie. The reason it's tricky is because we don't see the things that we need to see, or they usually see to make these things work. We don't see functions raised to powers. We don't see functions e's to the powers or anything like that. But with a little bit of manipulation, it makes it more clear. If I were to rewrite this as the quantity t to the 4th plus 4t plus 7 to the negative 1 times t cubed plus 1 dt, now I see my function raised to a power. And I can identify my u as that denominator, t to the 4th plus 4t plus 7. My differential du then would be 4t cubed plus 4 dt. Unfortunately, this doesn't match this perfectly, but I can just factor out that 4 and make it match. So 1/4 du would be our t cubed plus 1 dt, and things will be where they need to be. And then I have the integral of u to the negative 1 times 1/4 du. Move the 1/4 out in front. I have 1/4 times the integral of u to the negative 1 du. Integral of u to the negative 1 is going to give me, what's that going to give me? U to the negative 1. I can't add 1 to the exponent because that would make it 0. Logarithms. This is the natural log one. The natural log of the absolute value of u plus c. Natural logs. This is so much fun. I can't believe I get paid to do this. Back substitute. 1/4 natural log absolute value t to the 4th plus 4t plus 7 plus c. I wish I could draw the smile bigger, because that's how big I'm smiling right now. This stuff is awesome. All right, pattern recognition time. Take a look at the fraction. There is no exponent on either the numerator nor the denominator. Neither of those are wrapped up in parentheses with exponents on them. When you see a situation where you have a numerator and the numerator looks like the important part of the derivative of the denominator, the 4 that's missing I don't care about, but the variables and the terms and all that are there. When the numerator is the derivative of the denominator, natural log is going to show up. Okay? Lacking an exponent downstairs. There is no exponent. Oops. There is no exponent on this quantity down here. And because there's no exponent on that quantity right there, natural log. Okay? Another pattern to look for. Okay? All right, here we go. Let's take a look at this one. I see, control I'm doing composition. I always try to write the inside piece of the composition as the u and see if it works. So if u is t to the 5th plus 5, then the differential du is going to be 5t to the 4th plus 9. Oops, not plus 9. Geez, just 5t to the 4th times dt. Well, this doesn't match this, but I think it matches kind of, sort of. I can just get rid of that 5, right? Can I just call this 1/5 du is equal to t to the 4th dt? And now I think I got everything, so I'll do some substitutions. I've got the natural log of u. But wait a second, there's another u downstairs? And then a du here? Now if you're wondering where the du came from, the du here came from those two, right? The ones that are highlighted in yellow. And where'd this what happened? Where'd this natural log of u come from? Well, if we think of u as t to the fifth, there it is. It's right there and right there. So the natural log of blue over blue times yellow gives me natural log of u divided by u. Now, depending on how good you are at seeing things, do you see this as the natural log of u times 1 over u du? And guess what? We'll do substitution again. I can't use the letter u again because I already used it, so I'll say v. But wait, no. I don't need substitution. This is just, isn't this the derivative of that? So if I said that v was the natural log of u, then dv would be 1 over u du. And then I would have the integral of v dv. And the integral of v dv is going to be 1/2 v squared plus c. But what's v? V is the natural log of u. But what's u? U is t to the fifth plus 9. So then this becomes 1/2 of the natural log of t to the fifth plus 9 squared plus c. Oh man, that's a tricky one. So you know what I'm going to do? I'm going to erase this whole thing from this point down. I'm going to erase all this green. We're going to go back and redo that because I'm willing to bet that most people are comfortable to write there. All right. So I've done a problem, and now I'm looking at this brown integrand right here, and I'm thinking, hey, wait a second, there's a function, and that's the derivative of that same function. So if I've got a function and the derivative of the function, isn't this just going to be like the integral of f times f prime dx? And the integral of f times f prime dx is just 1/2 f squared? Because that's essentially what's happening here. I have something, v, multiplied by its derivative, dv. So I am taking the integral of v dv, and the integral of v dv is 1/2 v squared plus c. But if I do one back substitution, that's going to get me to 1/2 natural log of u squared plus c. And if I do my second back substitution, I'm going to get 1/2 natural log t to the fifth plus 9 squared plus c. Right? That's a tricky one. Right. Learn this though. Natural log of u over u du, the answer to that is 1/2 natural log squared. Right? Okay, we got a tricky one here. This is a mean one. Trust me, it's mean. Right? If you thought the last one was hard, then you're really going to like this one. Okay. I'm going to rewrite this, and hopefully when I rewrite it like other times, it'll become more clear. Do you see the natural log of x to the negative 1 being multiplied by 1 over 3x dx? And why did I write it like that? Because I saw a natural log, and when I see a natural log, I want a derivative to be a 1 over x. So I'm going to do a little bit of massaging with that. I'm going to clean that up a little bit, and I'm going to say that is going to be 1/3 times the integral of the natural log of x to the negative 1 times 1 over x dx. And why did I do what I just did? Well, because I've seen a problem like this before. I want this and this to be there, because now if I do a u substitution and say u is the natural log of x, then my differential du is 1 over x dx, and I can perform a substitution here. The 1/3 out in front has not gone away, and so I get this. Okay? Now, stay with me here because it's going to get a little confusing. This is now something I can take the antiderivative of, so I'm going to. This is the 1/3 that is out in front. The antiderivative of u to the negative 1 is the natural log of the absolute value of u, of course, plus c. But I need to do a back substitution, so what's u? Well, u is, by definition, the natural log of x. So then this is going to become 1/3 times the natural log of the absolute value of the natural log of x plus c. And that's our final answer. Okay? The rest of the problems on here are definite integral problems, so they're going to change a little bit. All right, so here we are. Evaluate a definite integral substitution. More practice. Again, looking at the patterns, I'm seeing a function raised to a power, so I think that's going to be my u. Then my differential du would be 2x dx. This doesn't match what I've got there, so I need to deal with that too. So I'm going to call that 1/2 differential du is equal to x dx, and now this matches, and I can perform my substitution. Whoops, I don't want that one. I get the integral of u to the 5th times 1/2 du, but I need to make some changes to my limits of integration. What will that new lower limit of integration be? It'll be 1. How am I getting that? I'm taking that and putting it into the statement about u and saying, well, if x is 0, what's u? 0 squared is still 0, plus 1 is 1. Okay? Similarly, for my upper limit of integration, what will that become? Again, I'm putting it into that statement over there and seeing what it works out to be. And it looks like if you perform that substitution there, 1 squared is 1, plus 1 is 2. Whoa, I don't want you. What do I want? I want this color. And so then now I've got something I can integrate. I'll deal with the 1/2 later. So that becomes 1/2 times the quantity 1/6 u to the 6th, evaluated from 1 to 2. So that's going to give me 1/12 times 2 to the 6 minus 1 to the 6th. Let's see, I don't know 2 to the 6 offhand, so I'm going to have to think about that one. Let's see, 2 to the 6 is 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 64. So 64 minus 1 is 63. So I get 63 twelfths. And so my value of my integral, 63 twelfths. I'm doing integration by substitution for definite integrals. Same thing as indefinite, just one extra step. We do that limits of integration business, and we just plug it in. All right, let's see if we can do another one. All right, here we go. I've seen this pattern before. I have a function in the denominator raised to a power. So when I'm thinking about this, I'm thinking of this as the integral from 0 to 1 of 1 plus x to the 5th to the negative 3 times 5x to the 4th dx. And when I write it like that, it's much easier to see the piece that's being raised to a power, or the function that's being raised to a power. So I'll make that my u. And then my differential du is going to be 5x to the 4th dx. And what do you know? That matches perfectly. Perform the substitution. So I have the integral of u to the negative 3 du. And what's my new lower limit of integration? It's 1, and my upper is 2. Again, I'm getting those by taking the old limits and putting them into the u substitution statement. Okay? And then all I have to do is just perform this integration. Well, that shouldn't be too bad. Let's see. This is going to become u to the negative 2, add 1 to the exponent, and then divided by that negative 2 out in front, evaluated from 1 to 2. So negative 1/2 times 1 over 2 squared minus 1 over 1 squared. Let's see, so that's negative 1/2 times 1/4 minus 1. So negative 1/2 times negative 3/4, 3/8, when it's all said and done. I kind of don't want to start this one because it's the last one. And if I do this, then I won't have any more to do, and I'll be so sad. Well, got to do what I got to do. Function raised to a power. There's my u statement. So u is 1 plus x squared. Differential du then is 2x dx. I don't have this over here. I have 5x dx. So how am I going to fix that? Well, how about 5/2 du is equal to 5x dx. Does that work? Perfect. This now matches perfectly what I've got, so I can perform my substitution. I have the integral of u to the 1/6 times 5/2 du. Lower limit of integration becomes 1. Upper limit of integration becomes 2. These are really boring substitutions for those limits of integration, but okay, it is what it is. And now integrate. 5/2 is going to hop out in front, so I'm going to get 5/2 times, add 1 to the exponent, I get 7/6. And so a 6/7 in front. And this needs to get evaluated from 1 to 2. Let's see, if I clean that up a little bit, what's that going to give me? 5/2 times 6/7 is what, 15/7? Cancel the 2 and the 6, make it a 1 and a 3, so denominator is 7, numerator is 5 times 3, 15. Multiplied by 2 to the 7/6 minus 1 to the 7/6. I have no clue what 2 to the 7/6 is. Let's see, it's the 7th power and 6th root, so it's 2 root 2. So that's going to be 15 over 7 times 2 root 2 minus 1. No, 2 times the 6th root of 2 minus 1. That's better. Okay, and there's my final answer. Of course, if they wanted some sort of a decimal approximation, I would just throw it into their calculator and get that decimal approximation. But we'll go from there. All right, this brings us to the end. There are no more to do. I feel so sad. I feel so terribly sad because everything is done and I got nothing else to do. I just saw something. I think this simplifies. Those both divide by 3. That's 21/4. Probably should have done that. All right, there's your extra substitution practice. I hope you enjoyed it as much as I did.